And the session is being recorded, so we'll post this online afterwards. Yes, I guess to get started, I don't know if Ian and Hamish, you want to briefly introduce yourselves, and then one of you take charge with a bit of an introduction to the geology of the area for someone from a non-geology background. And by the way, I've asked Jana to kind of be the buzzer for when we go into too much geological detail, which might not for everyone else. Okay. Cool. Over to you guys.
Go ahead, Hamish. Oh, Hamish has no audio.
Can't hear us.
Okay.
All right, I'll let you guys dig into that. Then I'll start talking. So my name is Ian Anderson. I'm a geologist. I work for OZ Minerals. I've worked for OZ since March 2010, so a little while now. I spent 3 years working at Prominent Hill on the exploration program between 2010 and 2013. And then I moved to the Carapatina exploration team, and I worked at Carapatina for 2.5, 3 years. Now I work in the project generation team, so my current role is to wander around and try and find M&A opportunities or exploration opportunities that OZ Minerals should and can invest into. So at the moment, I'm running a couple of exploration programs in Sweden, and in the last year I've been taking part in the exploration at Jericho, the new discovery with OZ Minerals in Minotaur in Queensland, and a few other small projects around the country. And then a bunch of research and I guess some experimental projects on the side. Is that enough for Hamish to get? Maybe not.
I don't think we've quite got it sorted yet. So maybe Ian, are you able to do the geology intro too?
Yeah, sure, I can do that. I guess I've been briefed that there's probably a lot of data science types as well as geologists on here, so I'll try not to get too specific. Look, the area that we've released data for, that's a Paleoproterozoic, mostly volcanic and metasedimentary terrain. That's all overlain by a cover sequence that's usually at least 70 to 300 meters thick. And the cover sequence is a bunch of sedimentary rocks that they post-date any known mineralizing event in the area. So it's basically a big package of not very prospective flat-lying, or mostly flat-lying rocks sitting on top of a package of very prospective rocks. But that separation between the surface and the prospective area, that makes it fairly difficult to actually go out and do the typical exploration programs, which would involve mapping of the rocks, going out and measuring structures and whatnot on the ground. It also makes it difficult to do soil sampling or rock chip sampling because there's just not any exposure of the basement to do that with. So I think that isolation there, that sort of creates a lot of challenges, but that also creates a lot of opportunities because we just don't have really in-depth knowledge of what's going on underneath that cover sequence. Yeah, I think that's sort of an easy way to look at it. There's probably more in-depth detail on the distribution of the rock packages and where they are, where they sit relative to each other, and the structures that divide those. All of that's going to be included in the data room. And I think I just heard Hamish's microphone.
Yep, I'm here now.
Awesome.
Got rid of the headphones.
Brilliant. So Hamish, do you want to give a quick intro about yourself, please?
Sure. So I'm a principal geologist for OZ Minerals. I've been working in mineral exploration since the mid-1990s. With regards to this project, I was involved from the early days with Minotaur and Billiton and the joint venture that we had. I was a member of the discovery team in 2001 that discovered Prominent Hill, which is the Marloo open pit. And then from about 2001 to 2009, I spent a lot of time both on the deposit area and also doing some regional exploration. We had a little bit more exploration success in 2007, I think it was, when we discovered Encarta, and that's one of the current underground operations. I'm currently working on other project generation activities within the company, but I do have a pretty reasonable knowledge of the history behind the project, going back to pre my involvement as well, so sort of back to the 1980s.
Cool, thanks, Hamish. So before, which you probably didn't hear, Ian gave a great introduction to the geology of the area. So we kind of started on the questions that we have had come through already, which some of which I sent you guys, and then we'll ask you, open it up to the participants to ask more questions. But I suppose one of the key things that people have been asking is, what have you guys done previously? What have you looked for in the past? And in that sense, like, what drove you to collect certain data sets? How did you collect them? How did you use them? What specifics around the anomalies were you looking for, and what features were you looking for?
Sure, I can talk to that with regards to some of the early stuff. The early work that was done by Minotaur Resources. We approached Normandy in the late 1990s. We had a backing from Billiton at the time, which was a big help in terms of what had been done previously by both Normandy and CRA. Majority of work included, well, there were some large-scale geophysical surveys, so 1 kilometre by 1 kilometre ground gravity over the entire however many thousand square kilometres. So that was all helicopter supported, I believe, and airborne magnetics. We actually didn't acquire any new data. So with regards to the gravity, there had been infill conducted over or completed over anomalous areas, like gravity highs. So we went in there looking at what the previous companies had done, and they drilled all of these magnetic anomalies and got hundreds of metres of sub-economic grade copper, so 0.1 to 0.3% over very long intervals in magnetite-rich, magnetite matrix hydrothermal breccias. So I'm thinking about prospects like Manxman, Joe's Dam and Taurus as examples. We went in with the view of obviously doing something different, so not necessarily drilling more magnetic targets because we were likely to get similar results. With the backing of Billiton, they were obviously only interested in sort of tier 1 type deposits. So the two projects that we had with them in South Australia were focused on Olympic Dam style iron oxide copper gold mineralisation, and another project was focused on Broken Hill style mineralisation. And so we essentially, in targeting for Olympic Dam, we went and had a rethink about what that geophysics of Olympic Dam actually told us. And it told us that the ore body itself was actually non-magnetic, but very dense, courtesy of the very high iron oxide content. And so we targeted gravity features that may have been closely related to magnetic features, and that's what actually led to the discovery. We didn't drill mag targets. Following the discovery of Prominent Hill, we spent quite a few years following up with further infill gravity surveys and drilling into other gravity anomalies. One of the things that we ended up finding, or we didn't actually discover any significant deposits outside of the Prominent Hill mining lease. But we discovered that the biggest contributor, even at Prominent Hill, a large contributor to the gravity feature is the paleotopography. So the variability in the thickness of the cover contributes a lot to that, to the gravity signatures. And so that was a big contributor to the things that we drilled, along with, if you go further north in Mount Woods domain, you get into high grade metamorphic rocks, which have a lot of garnet in them. And they can give you pretty high gravity responses. And then out to the east, we now think there's probably a big pile of Archean volcanic rocks, and they could include quite a significant amount of basalt. And so that would obviously contribute as well. So one of the things that we also did at Prominent Hill post-discovery was some IP surveys, induced polarization surveys, which showed very strong chargeability feature, perfectly coincident with the gravity anomaly. When we did downhole work, downhole IP work, though, what we saw is not a correlation between chargeability and copper, but a chargeability and iron. So it's actually the iron content, we believe, that's contributing to the chargeability response at Prominent Hill. And having said that, we still thought that IP was a good way of screening gravity targets. If you didn't have an IP anomaly, then you probably didn't have a big accumulation of iron oxides. And so we did quite a lot of IP over various prospects as well. We also tried EM at Prominent Hill, some downhole work, and the only rock that gave any sort of response as a conductor was the carbonaceous fault zones. So even the high-grade chalcocite didn't really give us much joy. And we tried pretty much every geophysical method there was. But the two that really stood out for us were IP and gravity combined. And so beyond that, we had other mineralization models, I guess, which we have thought about and gone and tested, particularly in the higher grade metamorphic rocks to the north. So we were interested in the possibility of there being Broken Hill type targets further north in the Mount Woods domain, where I'm not certain that is necessarily a valid model anymore, given that the age of the rocks are probably different from what you see at either Broken Hill itself or Cannington, which is the other Broken Hill style deposit, the large one in Australia. And then we had to think about, I guess, magmatic nickel sulfide. So to the northwest of Prominent Hill, there is a large mafic, ultramafic intrusive complex, which we call the White Hill, which is a major gravity and magnetic feature on the regional maps. It's variably made up of gabbros, ferrogabbros, anorthosites, magnetotites, troctolites in the middle, in the centre of it. And we have drilled some holes into that, but the rocks that we've intersected to date appear to be very rich in titanium and vanadium, so we're looking at the upper part of a chamber by the looks of it in those rocks. Probably not the ideal place to go looking there. And then we also checked out other models, given our experiences elsewhere in the world. So we knew we had a reasonably thick package of volcanic rocks in the structural footwall to the south of Prominent Hill. And within those domains, we see basically green rocks and red rocks. So we started thinking about, are there possible analogies with some of the manto type copper deposits that you'd see in Chile, copper silver as opposed to copper gold, probably very similar to sediment hosted copper systems, but just hosted in reduced or reduced and adjacent oxidized volcanic rocks. Yeah, so that's some of the thinking. There's, I guess, the other thing we've thought about is Archean VMS. So out in the Pluto, Halifax Hill area, to the about 30 kilometres to the east of Prominent Hill. Those targets will be deep though, so we're looking at several hundred metres of cover, and so you need a pretty decent sized Archean VMS to make it worthwhile. That's pretty much it.
Awesome. I think I wonder if it'd be worth, Hamish, for the non-geologists out there, is that, do you think if we kind of tell us a bit of a story about Prominent Hill in terms of how that mineralization may have formed, and then why some of those features, I know this is a hard question, but and then some of the features that you're kind of describing that you pick up with those different techniques, like why those features are highlighted in those techniques like gravity IP, just from a non-geologist point of view.
So, yeah, how was Prominent Hill formed? That's a really good question. It seems to be most of the copper sulfide minerals are contained, they're disseminated sulfides. So we're not talking, it's not a massive sulfide deposit, but it's relatively evenly distributed throughout the ore body, and is located in the matrix of breccias, which which makes the mineralization essentially stratabound. So they're restricted to a couple of key units, so these are what you might consider as early formed breccias. So they were there before the hematite and before the sulfide, and we have pretty good evidence of this now from drilling about 15, 20 k's to the west. We see exactly the same rocks, but without hematite in them, or much sulfide either. Copper sulfides. So it's
Can you explain a little bit like what an actual breccia is?
Okay, so a breccia is essentially like if anyone knows what a conglomerate is, maybe. So it's a rock which is made up of different size particles. So you might have clay size grains right through to sand size grains, which might, in this instance, would form part of a matrix, like an interlocking network. And then within that, you have big sort of pieces of rock, which we call clasts, fragments. And these can be rounded or they can be angular fragments. So it's a fragmental rock, a rock made up of different size fragments, generally.
So to summarise that, you'd basically say you're looking at some kind of host rock. That's what you start out with. And then you've essentially, as part of your mineralising process, you've had some fluid, something come through and basically together in the matrix. And that fluid contains the iron and the copper and the things that we actually care about that we're then
Yep. So what we think was originally in that matrix was probably a lot of carbonate minerals, which are very reactive. So when a hydrothermal fluid hits that, it replaces the original rock. And then the thing to note for the actual geologists who are listening here is that the actual copper sulfides are the last thing that happens. So you've got your hematite already there, pretty much.
Awesome. So in terms of what people can look for, and we've talked about different signatures like IP and gravity, so for someone that's not familiar with those kind of anomalies, how would you actually identify those within the data set? And what's kind of normal, not normal type thing, or is it just a difference in?
I think.
Yeah.
So the main data sets that we have access to across the whole tenement block are potential field geophysics, and that's going to be gravity and magnetics. There's more, I guess, more specific areas that have been concentrated on that will have IP and EM and some other techniques on them, including some mesola mass locally next to Prominent Hill. But in the broader sense, it's really just gravity and magnetics, which are the ubiquitous, I guess, coverage. So in those, I guess, the very nature of an anomaly is that it's anomalous. So if I tell you what one looks like, then you'll look for that one specifically. But realistically, the bulk of the rock package is going to have a density somewhere around maybe high 2.7s, 2.8s grams per cubic centimeter. Whereas if you get into a significant accumulation of sulfides, that should be ramping up into 3s, 3.5s pretty comfortably. So if you have maybe massive sulfides in a bunch of sediments, then theoretically you should still have a positive density anomaly, which will show up as a positive gravity anomaly in the survey. Having said that, though, as Hamish mentioned earlier, I guess the strongest control that we see on the distribution of positive gravity anomalies is the topography of the basement rocks. So on the surface, it's reasonably flat, but the surface of, I guess, the basement rocks, there's cliffs and mountains and valleys all hidden underneath the sediments on the top. So if there's suddenly a hill in the basement rocks, that'll also show up as a positive density anomaly. And so those false friends they're everywhere, and a lot of false friends have been drilled. So then with that gravity data set, you can run inversions, which you can constrain with the drilling locally. And so if you were to do, a depth constrained inversion, you could maybe start looking at, are any of these density anomalies truly in the basement, or are they coming from just variations in topography underneath? Again, similar things with magnetics. Magnetics they decay a lot faster with distance. So if you have something that's magnetic that's close to you, it'll have a very strong anomaly. And as you move it away, that strength of the anomaly decays very quickly, which I think even that exaggerates that effect of, if you have basement topography changes, you'll see a positive magnetic anomaly or it dropping off. But some things that I think are fairly common, if you look at sort of globally, what is an anomaly? It's more like, for example, if you have a trend of things, everything seems to be going in one direction, and then suddenly something goes in another direction, or there's a weird kink, or it's more changes that are, I guess, anomalous, but harder to pick out, because as humans, you look for the bullseyes, you look for the things that are, glaringly out of place. But the more subtle things that are out of place, they're more easily overlooked.
So can I ask a couple of questions there? I mean, have you guys used much structural constraints, so overall structural fabric in terms of looking for anomalies? And do you also use gradiometry methods, where you take gradients of those potential fields and use those to actually look for anomalous gradient behaviors?
In terms of structure, I would say no, we haven't used a great deal of that, but it's difficult to actually map structures until you have the drill core. Structural mapping was very useful in actually putting together the resource. We do, and also in a regional exploration sense, to actually map the different rocks, the different domains.
Wi-Fi, it will drop out altogether.
And what your other question was regards to,
like grav gradient and residual.
Yeah, so the thing that was done very soon after the original discovery was that we ran first vertical derivatives on the gravity and also a second horizontal derivative on the gravity, both of which really highlight where the biggest iron concentrations are. The second horizontal derivative in particular works really, really well, that Prominent Hill. Um, I've also heard that it works well at Olympic Dam, but I haven't seen the data. And so that's one filter, I guess, that you could apply to actually identify where iron-rich accumulations are. So yeah, going back to Ian's point, when we look at the gravity, it's not just a gravity high that we want. We want something which is high frequency. And so essentially, you know, if you draw a contour map, then the contours are really, really close together and you get a high over a short distance. And you see that when you start to use those filters even more so.
Okay, cool. So, so another question then is we've got a bunch of data scientists who are currently looking at using publicly available exploration data from around Australia to build data science models. Could you give us a sense of where you think there might be analogous regions of Australia that might be useful as other training locations, I guess, to what you guys see inside the Mount Woods tenement?
Good question. There are some similarities with perhaps with Cloncurry. I'm not talking about Prominent Hill itself, but the group of rocks just to the north, I think we've previously thought could be very similar in both composition and age to the Corella Formation. Is that right, Ian?
Yeah, so I actually just typed out an answer to a question where I was describing interbedded limestones and peelites, which we think are part of the host sequence for Prominent Hill. And those interbedded limestones and peelites, they bear remarkable resemblance in both, I guess, composition and layering to the Corella sequence and in Queensland. We also believe that the age of that sequence is pretty much the same as the Corella, and so it should at least, I don't think that they were connected as a facies necessarily, but yeah, we think they're synchronous and they both exhibit similar prospectivity for IOCGs and effectively most mineralization in both of the districts. I think training data in the Gawler, there's not too much in the Gawler that really stands out other than the IOCGs. There are sedimentary copper occurrences, which are usually flat-lying and I don't think very economic yet. I don't think we've found anything in the overlying sequences. Pretty much the big deposits or the things that are mined in the Gawler are either going to be iron mines, for example, like Cairn Hill or Peculiar Knob, and those also display a fair bit of similarity to sort of the IOCG and replacement styles as well. I don't think there's anything else that's really been found that's been mined in the area that you can find in the public data. Hamish can probably pick an example that I don't know about.
The only other deposit within Mount Woods domain that I can think of is Cairn Hill. I'm not sure how much information is on that, but that's probably be a marginal target for Oz Minerals.
That's a chunk of Cairn Hill. So it's all magnetite and chalcopyrite. I think the overall copper grade in this is fairly low. It was mined as an iron mine, and that closed in 2012, I think, somewhere around the time that prices started going down. So we smuggled this out of there on a field trip, but that's what it looked like.
So there's a couple of questions coming through in the Q&A. So the first one is a discussion around earthy hematite. Like, okay, what's the difference between that style of hematite and how it differs from the main mineralization and alteration?
Yep. Okay. Earthy hematite. Yeah, okay. So the earthy hematite, there's several different types of hematite at Prominent Hill. The the main one that actually hosts mineralization is a dark grey crystalline hematite. So you can actually, if you look with your hand lens, you can actually see the individual crystals of hematite in the matrix of or breccias or in veins, and within that hematite you have the sulfides. The earthy hematite is a really fine-grained red hematite. So if you wet it and rub your finger on it, it basically rubs off on your finger. You can paint your face with it like an ochre type of thing. That at Prominent Hill, we don't see that hosting a lot of mineralization. Some of the more recent, or some of the research that we did approximately 7 or 8 years ago suggests that some of that may even be hydroxide, so not pure oxide. So it's hydrated iron oxide. So it's almost like a possible weathering effect, very low temperature hematite. The other type of hematite is a steely hematite, and it's like it sounds, it's silvery grey, really fine-grained hematite, which is actually intergrown with cryptocrystalline silica, and extremely hard. So drill bits hate it, and there's not a lot of copper in that variety either, but we do get some high-grade gold zones within those rocks. So the earthy hematite, I guess to summarise, is not a main host of mineralisation at Prominent Hill, and it's, I would say, overall not a big contributor to the density or the gravity anomaly either.
Great. So another question we've had come through from Liho was that the Mount Woods tenements aligned to a magnetotelluric anomaly below 70 kilometres. What is your rationale behind that?
I was just typing up an answer there, but yeah, we see similar MT anomalies beneath Olympic Dam, Werder Well, and Vulcan, and those have been published in the literature. Recently, the state government has run a large MT survey across a big chunk of the Gawler, and they've called that the Oz LAMP survey. I don't know if that data's out yet, but we're seeing snippets of it at conferences being shown off, and we're seeing similar MT results as under other IOCG occurrences in the Gawler. I think that the rationale behind that, and this is a bit more interpretive now, but I think it is similar to like a kimberlite in a way. So you have a deep tapping, either structure or corridor that goes properly down towards the mantle, if not tapping into the mantle. And the charge of, or the conductivity anomaly that you see from that, that's probably coming from, I guess, more hydration. So a lot more fluid along that corridor, tapping from deep. So it's going to be warmer and wetter and thus more conductive. You've got interactions with the mantle and the near surface in those cases. When you see like the opposite in MT and you have a big like non-conductive block, that's something that's very old and dry and hasn't seen a lot of interaction with the deep crust in a very long time. So yeah, I think that's what I would interpret it as.
And we had a question come through from Matt around your approach with the seismic data. I said that there's been some seismic data was acquired, but only a few lines. Was there any consideration of using 2D regional seismic, say 20 lines over 100 kilometres at 5K spacing to map the sediment basement interface, and then use this in gravity inversion?
No, our main reason for doing those lines was to understand the basement architecture a little better. We know that the rocks that host Prominent Hill are overturned, but we wanted to know where the southern boundary of the host rocks were, where the southern boundary of the Gawler Range volcanic equivalent rocks were, and what was south of that. And I think that was successful and showed us where the key terrain boundaries were. and it just so happens that Prominent Hill is right on one. In terms, I guess, with so many drill holes in our regional database, we've actually been able to put together a pretty reasonable depth to basement map as it is, so we can actually use the drilling. Ian, have you got any comments on that?
Yeah, so the seismic survey, I think that was done, it was recently late in 2012, maybe mid 2012 from memory. In 2013, exploration slowed down quite a bit in the Mount Woods region. So we'd acquired Carapatina, we made the Camson discovery, and there was a bit of a downturn in the industry at the same time. So our exploration team shrunk by quite a bit at that point. So what really did come out of that seismic work is, like Hamish said, sort of the broader architecture. It changed the way that we interpreted, I guess, the sequence of events that led to the current morphology of the inlier, and it sort of changed a bit, and at the same time confirmed some of our interpretations about the formation of Prominent Hill and where that sat on a structure and so on. But no, it hasn't been used that I know of. I mean, somebody's probably already done it, but it hasn't been used to really constrain the gravity maps or any of the gravity inversions in that regard. So there's potential opportunity in that.
Just to butt in there, sorry, is that in the immediate area around Prominent Hill and Neptune, that has been done. So we have gone back and remodeled our gravity. We have 3D inversions taking into account the paleotopography within that Prominent Hill to Neptune area.
Yeah, that was done with drilling.
Yeah.
Right. So yeah, sorry, at the prospect scale, there are prospects that have been constrained, but sorry, I misunderstood. On the big broad scale, no. There's another question in the chat as well, asking about have the tenements been mapped for paleotopography? Sort of, but really no. There are areas where there's a really long distance between drill holes, and even though there's quite a few collars, in some areas those collars didn't actually push through the basement, and so the actual depth is, I mean, we know how deep it is at least, but we know how deep it actually is. To follow that, there's a question, can the change in gravity gradients, for example, a second derivative caused by paleotopography, exceed the gradient caused by Prominent Hill? That's an ambiguous question as well.
Yeah, that's a hard one.
So,
I guess I can comment that the main, there's an old image that's been published quite a few times, which shows a ground magnetic image with the second horizontal derivative gravity contours. And if you take that long sort of roughly east-west striking gravity feature, then to the west of the discovery hole, there's minimal variation in thickness of the cover, and the iron-rich rocks still really stand out there. So yeah, it's a difficult one to answer.
So slightly on a different tack, we had a question from Barry asking, is vanadium a viable target in White Hills?
Not for Oz Minerals, maybe for another company.
Fair enough. And Craig would like to know if there's any obvious alteration halo around the hill. The northern limit of the ore body is, I guess, what we would call the hanging wall fault. You step north of that and you go into a magnesian magnetite skarn. So we have talc, tremolite, magnetite, pyrite, alteration of metasediments. So that's much earlier, we think, than Prominent Hill.
We've actually dated the pyrite from that, and it's around 1635 million years, something like that. So older than Hilterberg Gawler Range volcanic rocks. To the south, though, where you're basically staying in the hematite system as you go from south. So the ore body itself is hematite, sericite, a bit of chlorite and carbonates. South of that, you keep seeing hematite, I guess. Geochemically, there is something that's very useful, and that is the sodium. So if you have a look at a section through Prominent Hill, if you go far enough south of the deposit, your sodium levels pick up to plus 1% in the assays, and that pretty much demarks your limit of alteration away from a Prominent Hill type ore body. So you'll start to see albite coming in. So that's still alteration. Albite altered plagioclase phenocrysts, and they'll come in the basalts and andesites.
Another, maybe not necessarily as an alteration halo, but something that we do see, I guess the blue duck group sediments, which occur to the west of Prominent Hill. We do see a number of quartz calcite veins that have a fair bit of fluorite and chalcopyrite in them, which some of that has a bit of the flavor of Prominent Hill, but you can really call that an alteration. Those veins just sort of crack open and they have a very small alteration or wall rock change around them, but there is a bit of that flavor that also extends, a few kilometers away.
That's a good point, Ian. The other thing I forgot to mention is in the skarn to the north, so across the Hanging Wall Fault to the north of the Prominent Hill ore body, there are veins of carbonate, calcite, fluorite, hematite, chalcopyrite. So actually around, even before the discovery, we felt that this target was particularly attractive because it did have this late stage, more oxidized overprint as opposed to higher temperature alteration only. So that was always encouraging, as well as having the geophysics targets.
Right. So I think we've touched on this question a little bit already, but something came through on the forum around asking, is Prominent Hill mineralization structurally controlled, and what structures are they? So I've mentioned about the breccias, but maybe the overall structure we can touch on a bit more.
Sorry, I missed that, Holly. What was the...
Just a question that came through is asking, is Prominent Hill mineralization structurally controlled? And if yes, what structures?
I would argue not obviously. I think there are probably structures that are important. They're pretty difficult to see. For example, if you have a look at the open pit, there are structures mapped, but they really don't displace mineralization all that much or control mineralization. The mineralization just seems to go straight through in a particular rock unit or a couple of rock units. So I think there's a stronger stratigraphic control than structural control in this instance. I'm not sure if Ian has a different view on that, but that's my view.
No, I'm fairly happy with leaving it there. There's a question here from John Anderson, who I'm guessing is the John Anderson, asking about prior concepts and targeting rationales. I think I sort of alluded to it earlier, but our last big push of exploration in the area, with the exception of a few smaller programs, the last big push for exploration pretty much tied off around the end of 2013 under the reporting clauses in the essay. All of our annual technical reports should be available publicly for all of those years now. So that's out there, and you can see what we were after and what we were doing during that time. But I think that sort of alludes to another question that came through, I think, on the forums as well. And I think this is a pretty good time to answer it. And the question was, why haven't we found anything, considering we've been working there for 10 years? we found stuff that there's been things found, but there's a few things that I think create the opportunity here for the competition. So instead of bragging about all of our sub-economic findings, what I'd probably like to say is that there was a lot of research done at Prominent Hill because we have access to an IOCG and we have access to all of the drilling and everything else. So we ran a concentrated research group in-house and developed a lot of IP around IOCGs and the Gawler. And as part of that, we built up a big, I guess, a fairly comprehensive model of where we would expect to find an analog or a similar deposit to Prominent Hill. And so that model was very, I guess the exploration program became very model driven for a period of time while that model was, I guess, thoroughly tested. And you can see the pattern in the drilling if you go and think about it in that respect. You can see the pattern in the drilling for the last maybe 3 years from 2011 to 2013. You'll see exactly where we were and what our model was and what we were testing there. What we didn't do during that time is step away consistently. So we didn't take a serious look at some of these other mineralization styles that we think are prospective in the area. The other constraint that we had at that time as well was that Prominent Hill was, it had a limited mine life at the time. So we weren't getting as much resource to reserve conversion. We didn't have the mine life pushing out year after year as it is now through the great success of the people working at Prominent Hill. And so we were very focused on finding something within a short distance from Prominent Hill. And that's the other half of what you can see in our drilling is we were focused within maybe 16, 20 kilometers of the mine itself. And so there's that massive license package further off to the north and east that really hasn't had as much attention as it probably deserves. So while we did thoroughly test our models and we did have some success during that period, there are a lot of areas where models have been conceptually put together but never thoroughly tested. I don't know. Hamish, why haven't we found anything?
I think just, we haven't found anything because where we've drilled, there hasn't been anything.
Good answer.
I guess when thinking about those northern areas, it's important for people to keep in mind that the metamorphic grades there are significantly higher than what we see for IOCG deposits, the known IOCG deposits in the Gawler. And it's important to keep that in mind when you start thinking about any particular type or model for base metal mineralization.
Yep. Yeah, so I guess that sort of ties into what I was saying. I mean, and then there's another question that came through in the forums that probably ties to this as well, which is saying, like, why do you think other people can find something that we haven't? We have extensive IOCG expertise within the company, and our team of geologists were pretty much all experts in that type of deposit. But we have our models and we have our thoughts, and we're far enough down that path that it's always going to be tickling in the back of our mind. And so if people can come and look at the data with a fresh set of eyes and fresh perspective, different models can be put together, different ideas can be presented. And, if a model and an idea is put forward that makes a lot of sense, then those are the sorts of things that we're interested in seeing. And that's the sort of thing that we'd like to go out and test as part of this competition. And there's another question that asks something like, there's a lot of data scientists and a lot of geologists involved in this competition, and how does somebody get an advantage? And really the advantage there is what Hamish said at the very beginning about the discovery of Prominent Hill. You have to come in and look at the area and think about it differently and put together, a model and set of ideas that sort of break the norm from what's normally been explored for and normally been done there, and look at it from a different angle. I think we had a really good experience with Minotaur with the joint venture that we had at Prominent Hill in 2016 and 2017, where they came in and applied a different exploration model for sort of an iron sulfide copper gold. And we tested a few targets in structures and areas that if we were out there looking for IOCGs, we would have never drilled there. We got some proof of concept, we got some good results. We didn't hit an economic ore body, but I think that really highlighted the potential of having people come in and look at things from a different perspective. And as a result, we're opening this up, at a broader scale. So I think that's how you'll get the advantage and find the things that we haven't found yet.
Awesome. One slightly more specific question coming through from David, which was, what's the age constraint on the hanging wall fault relative to mineralization?
The most recent movement on the hanging wall fault is post-Permian and pre-Cretaceous. Okay. So we have cover units. We have a basal cover unit, which is Permian in age, and the hanging wall fault actually comes up into that, but it doesn't extend into the Cretaceous shales that sit on top of the Permian. What was the original age? I don't know. Whether it's I assume that it's been reactivated at that time, and it was much earlier than that.
Then I suppose kind of looping back to what Ian was saying, and I'll ask Jess maybe to comment on this, specifically from that machine learning perspective. When we've spoken to some data scientists, they've kind of commented on, well, if someone's already built a machine learning model to predict mineralization, why can't they just use that for everything? So Jess, can you please explain why that is not the case?
Sure. Well, I mean, my feeling is look, I think Ian and Hamish have touched on this, that we don't often have enough constraints to really constrain a machine learning model to the point where we've got tons and tons of training points. If you think about the Mount Woods tenement, you've got one economic deposit, which is Prom Hill. You've got a bunch of sub-economic deposits or locations of mineralization, which you guys have talked about some of those. So trying to come in and say that in this particular case, I can apply a model from somewhere else is fraught with difficulty. So I wondered whether you guys could give us some insight as to where you guys currently have data challenges, potentially with things around visualization or communication of lots of data layers. How do you guys sort of currently do that workflow, and where do you think there might be some improvements that could be made as practicing exploration geos?
You say practicing like we're professional doctors or something, but
Well, practicing with me anyway.
Yeah, I think that the exploration data analysis that gets done, as part of the day-to-day as a geologist, it's not necessarily a firm workflow, probably for the same reasons that you just alluded to, saying that having one specific machine learning algorithm and applying that to all areas, that doesn't really work. The only time that's going to work is when we can surround the Earth with sensors and invert the whole thing, at which point we'll be out of a job and hopefully retired by then. But yeah, I think the key term there is exploration, exploratory data analysis. And so a tool that we use quite frequently, and I'm trying not to plug too many vendors here, but Reflex has a good tool called AWST, and it's effectively Excel that lets you color things up and graph things, and whatever you color on one graph gets colored the same on others. And so you can plot histograms or scatter plots or whatever else of your data and pick things that look interesting or anomalous and really quickly see how those compare to other variables in your geochemistry or whatever it is you're actually looking at. But these sorts of tools, they're really useful and powerful, but they're fraught with a couple of dangers. And so one of the big dangers is, as humans, we like to see an anomaly and then think, well, that's the solution or that's the only thing to be looking at. And then you just end up focusing in and you end up just seeing sort of one tree for the whole forest. And you miss a lot of things that are still there and the data is trying to tell it to you, but your bias at that point, maybe your personal bias or your confirmation bias or the fact that you have a deadline, that keeps you from exploring the rest of the data. And I think that's something that in the machine learning space and applying more algorithms or more fuzzy logic to the data to really start pulling out anomalies that aren't enrichment but are depletion, or anomalies that are not the first order anomaly, but something that's a couple of layers down that isn't screamingly obvious. Finding those things and visualizing them and pulling them out would actually give probably more insight into problems that we all think we've already solved.
So if you're a data scientist and you're looking at a way of getting an in on some of this aspect, then taking a good look at manifold learning and anomalies off the back of manifolds would be awesome. Sorry, just translating what you said there, Ian, into data science language or ML language. But yeah, there's a big sort of manifold learning problem baked into all of these that would be really interesting to have some.
Sure. Just to clarify, as far as Hamish and I know, a manifold is the thing that bolts onto the back of your car engine and sucks the exhaust out. So there's your advantage.
Yeah. If you're a geologist and wondering what that means, it'd be like saying, say I had an alteration trend in space. What I want the computer to do is learn what that alteration trend is so I can remove it and then look at deviations from that alteration trend that might be indicative of mineralization. So I think I've translated both ways now. Probably.
Thanks for that.
It's like Google Translate.
I'm getting my money's worth out of this now. Good.
Awesome.
All right. Oh, we've got some more questions. Another question come through. According to the website InfoGeo, are working on ML. Is there a report for findings? Oh, yeah, we'll probably have to check the SARIG website to see where they're at. I think they have released a few things on MT recently. So I wouldn't say you'd be disadvantaged as it's only been released to the public recently. I think it was released before the start of the competition.
Yeah, there are statewide depth slices out of that MT data that are available on SARIG. I plonked the links into the chat there for everyone to grab. If you have any trouble getting hold of those, please let us know. We have some good contacts at SARIG that have been very helpful at releasing some of their larger data sets for us to stick up on our data portal. So if there's something in particular that you want that seems a bit hard to find in the SARIG portal, let us know and we might be able to make that a bit easier for you.
Awesome. Give people a couple of minutes to hammer in any last questions as we close up. Yana, you wanted to mention something from the community?
Yeah, sorry. Just a reminder that we do have that teammate expression of interest form and a spreadsheet you can browse. So perhaps if you're either a geo or a data person listening to this and at various points becoming despondent because of everything, I didn't know where to start. There were so many points in this, but I just looked at Polly and Jess. Yeah. Look, I did first year geology, okay? But yeah, this could be a really great starting point to find some of those other geologists or data scientists on that spreadsheet and say, hey, I heard Ian talk about this thing, which sounded like it could be cool, but I have no idea. Can we explore that? So just a reminder to use that team spreadsheet. We'll keep sending links out about it. And if you need any help getting those kind of team things happening, just let us know. We do want to help if we can.
Awesome. And just another question from Dave on there. Just looking at alteration codes for hematite, see HTG for hematite dark grey as well as HSG for hematite steely grey. Which of these is the alteration Hamish said was mineralization?
We need a question as well. Which
can you guys see Ian and Hamish? Can you see that question from Dave?
Yep, got it here. I think Hamish is. Oh, there we go.
Sorry, I've just took myself off mute. It's HDG will be hematite dark grey. So that's the crystalline hematite that hosts mineralization. The HSG is steely grey, and there should be one HR.
I think it's HRE.
HRE, red earthy. Yeah.
Yeah, and there is data dictionaries in the data set as well, so everyone should be able to read through those. So two more. So which is the best data set to model other than MT?
Yeah, that's an easy one to answer. Just model copper, find where there's lots of it, and tell us, and we'll give you a prize.
And Matt has asked, has there been any exploration for sediment hosted copper, zinc, etc., and overlying sedimentary rocks?
Look, I don't think that Oz has explored for that. There's been exploration for coal and gas, and I'm presuming oil as well in the host sequence or the sedimentary sequence. So, they would probably log any copper that they found as a contaminant and throw it away. But no, as far as I know, I don't think there's been a comprehensive sedimentary copper or zinc in the overlying sedimentary rock exploration program.
If you're interested in looking at some of the previous explorations happened, we've just put a dump of 130 gigabytes worth of exploration reports from CERN up on the data portal. So if you want to do some NLP or text mining on those, then that might be a good way to find something that
dump is such a negative word.
Well, it is. It's a dump. They're all PDFs. But,
treasure trove.
That might be a good place to look for exploration things that aren't within the OZ Minerals data.
Cool. All right. Any last words, Ian and Hamish?
If anyone wants to ask a question verbally as well, you can raise your hand or ever hold the piece.
No. All
Yeah,
right.
No, I think we'll just leave it at that for today. Are we going to do another one of these, Holly?
If you want. We can.
We'll
Get some more questions coming through. So look, for everyone, thanks very much for joining today. Please keep putting your questions forward on the forum. That's really the main place in between these webinars to post any more questions that you have. And we're the Unearth guys here. We're curating those, so we're making sure those get passed on to Ian and Hamish and the other guys at Oz who have been dealing with the data and getting it all ready.
So if you want another webinar, let us know in the forum. Or if you don't want geology webinar and you want yes, then let us know, because we will organise those. We just need to know what is going to help you guys.
Yeah. But look, thanks very much, Ian and Hamish. I think that was really, really useful for everyone to get a lot more context on the geology and be able to hear from you guys directly. So really appreciate your guys' time. And yeah, I'm sure everyone else does as well. So thank you very much.
Well, thank you very much for giving us the opportunity, and thanks to everyone that connected and joined in.
Thank you
and
all.
We will post the recording of this live. Cool. All right. Thanks, guys. Bye, everyone.
Okay.
Bye.
Thanks. Goodbye.